Corrective eyewear, such as glasses and contact lenses, are an application of what we've seen when light refracts through a lens. When light changes mediums, it refracts, changing the angle that the light is perceived. This is why images appear larger or smaller through a lens. The human eye is curved and acts like a lens. So during normal vision, we have two important points. The near point is the point nearest the eye, at which an object is accurately focused on the retina. This is the closest point that you can see something clearly. The far point is the farthest point from the eye, at which an object is accurately focused on the retina. So this is the furthest point that you can see. This is based on the focal point of your eye, or focal length of your eye, as well as the distance of the object, in order to create the proper sized image in your eye. So everything inside or between the near point and far point should be in focus. Everything that's too close or too far is going to be out of focus. These objects are hard to see because although an image is created, it's not a focused image. We can use things like telescopes or microscopes to see further or closer. People who have nearsighted vision have a far point that is closer than normal vision, which makes it harder to see objects that would otherwise be in focus. When we calculate nearsighted vision problems, we're going to use the distance of the image and assume it is negative. If we're given a far point and we know the person is nearsighted, we're going to take that far point and just make it negative. The object's distance, we would use infinity, or in this case use a large number like 9 times 10 to the 20th, a number that's so big it might as well be infinite compared to what we can perceive. The focal length ends up being negative, which makes this a diverging lens. Corrective eyewear places the image inside the far point, so it corrects what's already going on with the eye and moves that image. It does this because we have two lenses that are interacting, the lens in your eye and the lens in the contact or glasses. Let's look at an example of nearsightedness. A nearsighted person has a far point of 60 centimeters. So that means the distance of the image has to be negative 60 centimeters. If we want to correct this nearsightedness, that's where we want our image to be placed. The distance of the object we're going to assume is infinite, or you can use a large number. We're going to end up using this formula. It's asking me to find the focal length, and we've used this focal length to then create the prescription of your glasses or contact lenses. In this case, we're assuming it's contact lenses. So here's our derived formula. It's based on the original formula, 1 over di plus 1 over dou equals 1 over f. Substitute the values you know. Dou is going to be an infinitely large value, so I use 9 times 10 to the 20th, a very big number. My di, my distance of my image, is negative 60. We know this because it's a nearsighted person. You take the near or the far point and you make it your negative di. Now it's just a matter of doing the order of operations. I'm going to simplify the top, simplify the bottom. This makes calculating the final answer a lot easier. Think order of operations. The top is grouped, the bottom is grouped, or the numerator's grouped, the denominator's grouped for this rational expression. When I evaluate my numerator and my denominator, I get this. Now, I included these values as scientific notation. Your calculator will probably spit these values back in scientific notation. It may not say times 10 to the 22nd. It may say negative 5.4 E22, 8.9 E20, which is just calculator language for scientific notation. Once I divide those two values, I end up with negative 60.7 centimeters. This is the adjusted focal point, or focal length. Because I end up with a negative focal point, I know that I have a diverging lens. Nearsightedness is corrected with diverging lenses. Far-sighted vision is the opposite of nearsighted. With nearsightedness, we moved the far point. With farsightedness, we're moving the near point, which means now only objects between the near point and far point are in focus, which makes objects that are a little closer harder to focus on. This happens naturally with age. As you age, your eye, or the lens in your eye, starts to deform. And this changes where your near point is. This is why a lot of adults or older adults end up wearing reading glasses so they can read something closer, like a book that's within or no longer within their near point and far point. When we calculate farsighted vision problems, the distance of the image is the negative near point. So if we're given the person's near point, we can find the negative image. The distance of the object is the distance of the object that you're looking at. Focal length is going to be positive in this case, which makes it a converging lens. So we correct this with converging lenses. Corrective eyewear places the image past the near point. This puts it within range of the near point and far point, just not your natural near point, far point. Let's do a far-sighted example. Person holds a book 30 centimeters away from their eye. Their near point is 50 centimeters. What focal length should be used to correct for this problem? So we're finding the focal length of the glasses, the focal length of the contact lenses. The distance of the object, the DO, or D sub O, is the distance of the object you're looking at. I'm looking at a book that is 30 centimeters away. So therefore, my DO is 30 centimeters. The near point tells us the distance of the image, but I want to see the image. Remember, the image is created on our retina, inside of our eyeball. So it's going to be at 50 centimeters, or negative 50 centimeters, because we take our near point and make it negative. That gives us our DI. Just like with nearsightedness, we take our far point and make it our DI, but make it negative. Now I'm trying to find the focal length. I have formulas for that. 1 over DO plus 1 over di equals 1 over F. I can find the derived version of that. If I'm trying to find the focal length, it's DO times di divided by DO plus di. Now, because there's no scientific notation, this calculation becomes a lot easier. I simply substitute in my values, 30 times negative 50 over 30 plus negative 50. To make the calculation a little simpler, I'm going to simplify the top, simplify the bottom. 30 times negative 50 gives me negative 1500. 30 plus negative 50 gives me negative 20. And I just divide those out. I end up with 75 centimeters. So the focal length of the corrective eyewear, in this case contact lenses, is going to be 75 centimeters. If we create a lens with a focal length of 75 centimeters and put it in front of a far-sighted eye, it'll create an image within the right far-sighted to, far point to near point range. We also see that because it's a positive focal length, it's converging lenses. The examples we've looked at so far are contact lenses. Because the contact lens is directly on the eye's lens, we don't have to worry about a distance in between them. If glasses are worn, you're going to add 2 centimeters to the DO and the di, the distance of the object and distance of the image. Now in the case of the distance of the object, we're moving the lens a little bit closer with glasses. It's moving 2 centimeters away from the eye, which means it's 2 centimeters closer to the object. So now our distance to the object is 2 centimeters shorter. For the image, we're going to add it. So negative 50 plus positive 2 is going to give us negative 48 centimeters. Because that lens was moved 2 centimeters forward, that image is going to be moved 2 centimeters forward as well. Even though we went from 50 to 48, that number actually got bigger or greater.